Everyone, I'm McCabe Levingood, and today we are going to do the Physics 2211 Lab 5 on the falling Slinky. We're going to go ahead and get started with a quick introduction. The purpose of this lab is to examine the motion of a falling Slinky. We're going to do this using tracker, and then we're going to do some computation. So we're going to compare this experimental and computational data regarding the motion of the Slinky. Some key physics principles that we need to keep in mind throughout the lab are the momentum principle, drag force, tension force, and gravitational force. The momentum principle explains how forces cause the momentum of a system to change over time. The drag force is the resistance offered by a fluid like air or water. And the tension force is a force experienced by a rope, string, or cable when it is pulled from the opposite end. In this specific scenario, the tension force is provided by the spring force within the Slinky. And then we also have the gravitational force, which is the universal force of attraction acting between all bodies of matter. Okay, here's some formulas that we're going to need for the lab today. Many of these formulas are derived from the momentum principle that we just talked about. So we have the velocity update, the momentum principle itself, and then position update formula. In the middle on the left, we have the tension force formula. And in the top left corner, we have the drag force, and in the bottom right corner is the gravitational force. Now we're going to get into the actual lab portion. So first we're going to start off with the experimental method. The system is the Slinky and the Earth. The surroundings are nothing, and then the mass is 0.225 kilograms. I have some data from tracker on the left and then a picture from tracker on the right. Okay, so now we have the computational method of the lab. Starting on the left, on line 36, I put in the ball's mass, and then on line 39 and 40, the initial conditions of the ball. Moving down, I have the 9.8 meters per second squared for gravity, the j hat vector, the b value for drag force, and then moving down from line 67 to line 97, we have the first calculation loop, and this takes into account gravity and drag force. So we have a bunch of equations. We have the force of gravity, the drag force equation, velocity update formula, and position update formula. And then lines 98 through 119 are another calculation loop, and this takes into account gravity and then the tension force. Again, we're just plugging in formulas into the code. We have the gravitational force formula, tension formula, and then velocity update, position update, and so on. So now we're going to compare our experimental and computational data. As you can see, initially the graphs are pretty much exactly the same. This was because in the video, the Slinky was initially at rest, and then after some time, you can see they kind of begin to branch off and differ from each other. This is likely due to human and experimental error using tracker with selecting all the points, and then also possibly a calibration error. Now we have the big question, why does the bottom of the Slinky stay stationary? In the video, the top of the Slinky accelerates downward due to gravity and meets with the bottom of the Slinky, but the bottom of the Slinky stays stationary. And this is because the Slinky is experiencing a tension force caused by the spring force within the Slinky, and that pulls upward. And then the force of gravity is also acting on the Slinky, which pulls downward. The tension force in the plus y-hat direction is equivalent to the gravitational force in the negative y-hat direction, and this causes the bottom of the Slinky to be in a state of static equilibrium. And in static equilibrium, the net force is 0 and the object remains stationary. So in this case, the bottom of the Slinky remains stationary. And that is why it does not move. Thank you so much for watching.